Now let us talk about the wave function. What kind of conditions should be satisfied by this wave function psi? Now the very first important point is that the value of this wave function, if for instance psi, suppose its value at any instant of time is infinite for some particular point. What would that mean? Infinite. It would mean that an infinitely large probability of finding the particle at that point, infinitely large probability of finding the particle at that point, and this would certainly violate Heisenberg's uncertainty principle. Therefore, psi must be finite or zero at any point. The next important point is that it must be single valued. Suppose psi has more than one value at any point. Suppose it has two values, for the sake of argument, two values. What would this mean? It would mean more than one value of probability. There will be two probabilities of finding the particle at that very point. The point is at that very point. It's like having electric line of force E1, electric line of force E2. They can never cross each other because at the same point, electric field cannot have two values. It goes exactly like this, that here we are dealing with probabilities. So this psi must be single valued, because if it has more than one value, at that very point we will have two probabilities for the same point, which is obviously inaccessible. And then the third important condition is that this wave function, this psi, should be continuous everywhere. I mean, this is necessary from Schrodinger's equation point of view, which shows that the double derivative of psi with respect to, say, x, it must be finite. It must be finite everywhere. It must be finite everywhere. And that's possible only if this d psi by dx has no discontinuity. It has to be continuous for this to be finite. So this d psi by dx has to have no discontinuity at any boundary where there is change in potential. And the existence of d psi by dx as a continuous function automatically implies that psi is also continuous. It is too continuous across the boundary. Now, this requirement, this is the fundamental. This is another condition that has to be satisfied by the wave function. So these three conditions that I talked about, they are playing a very significant role, very pivotal role in getting some information from solving Schrodinger's wave equation. And on acquiring, if these conditions are fulfilled by an acceptable wave function, it certainly carries a great significance. Now suppose we solve the Schrodinger's steady state equation, and And when we solve the equation for any given system that we have, for any given system that we have, and we solve it for that system, and the fact is that this wave function should fulfill these requirements. And then what we find is that the equation can be solved only for it can be solved only for some specific values, only for some values of the energy of that system that we have. And thus, the quantization of energy, only some values, and then automatically this energy quantization appears in the wave mechanics, and it appears naturally. It appears in wave mechanics as a natural feature of the solution of the wave equation. And the values of energy that we have, the values of energies that we have now by solving the Schrodinger's wave equation for some specific problem, we call these energies as eigenvalues. These values are termed as eigenvalues. And the wave functions that are corresponding to these eigenvalues, these corresponding accessible things they have the corresponding accessible wave functions, and we call those functions as, say, psi1, psi2, and psi3. We call those wave functions as eigenfunctions. That's it.